Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. A timeline of atomic models. This section explores the groundbreaking experiments and theories that have revolutionized our understanding of the atom's structure and behavior. John Dalton's atomic model. In 1808, John Dalton proposed his theory about the atom that matter is made of small individual atoms. Atoms can't be subdivided, created or destroyed, so it is a solid sphere. Atoms of the same element have the same properties. Atoms of different elements have different properties. Atoms of different elements can form compounds. Thomson's plum pudding model. In 1897, Thomson discovered the electron and went on to propose a model of the atom that an atom is electrically neutral. It has no charge. In an atom, both positive and negative are equal. An atom is made out of a sphere of positive charge, with negatively charged electrons embedded in it, rather like raisins in a pudding. This became known as the plum pudding model. Joseph John Thomson won a Nobel Prize for his discovery of the electron. Rutherford's nuclear model. In 1909, Hans Geiger and Ernest Marsden did an experiment to test the plum pudding model under the supervision of Ernest Rutherford. They concluded that atoms are mostly empty space. Most of the mass is concentrated in the center of atom. This tiny, dense, positively charged core called a nucleus. Electrons are closed outside the nucleus. Rutherford's model said nothing about what was inside the nucleus. Rutherford's experiment. A beam of alpha particles was directed at a thin gold foil suspended in a vacuum. A vacuum prevents to ionize between alpha particles and air particles. They expected the alpha particles to travel through the gold foil, and maybe change direction a small amount that would support the prediction of Thomson's model. But they discovered that most of the alpha particles passed straight through the foil. Some of the alpha particles changed direction, but continued through the foil. A few of the alpha particles bounced back off the gold foil. The bouncing back could not be explained by the plum pudding model, so a new model had to be created. This was the first evidence of the structure of the atom. When alpha particles are fired at thin pieces of gold foil, the majority of them go straight through. This happens because the atom is mainly empty space. Some are deflected through small angles. This happens because the positive alpha particles are repelled by the positive nucleus, which contains most of its mass. A very small number are deflected straight back. This is because the nucleus is extremely small and dense. Rutherford's model can be concluded that the atom must be largely empty space, with its positive charge, and most of its mass concentrated in a tiny nucleus at the center, and the much lighter electrons orbited the nucleus. Atoms and ions. Normally, atoms are electrically neutral. This means they have the same number of positively charged particles and negatively charged electrons, cancelling each other out, so the net charge is zero. This is called the neutral atom. When an atom loses the negatively charged electrons, it becomes a positive ion. When an atom gains the negatively charged electrons, it becomes a negative ion. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. A timeline of the nucleus's structure. This additional information explores the groundbreaking experiments and theories that have revolutionized our understanding of the nucleus's structure and behavior. In 1909, Rutherford's nuclear model. Rutherford's pioneering experiment proposed a model of the atom with a dense, positively charged nucleus at the center. However, this model didn't delve into the composition of the nucleus itself. In 1919, uncovering the protons. A decade later, Rutherford conducted another crucial experiment. He bombarded nitrogen gas with alpha particles and observed the ejection of positively charged particles. These ejected particles were identified as protons, revealing a key component of the nucleus. In 1932, unveiling the neutrons. James Chadwick made another groundbreaking discovery. He identified the presence of uncharged particles with a mass similar to protons within the nucleus. These uncharged particles were named neutrons, completing our understanding of the basic building blocks of the nucleus. James Chadwick won a Nobel Prize for his discovery of the neutron. Therefore, we can conclude that the atom has a central nucleus. It made up of positively charged protons and uncharged neutrons, which are called nucleons. The structure of the nucleus in atom. There is a central nucleus made up of protons and neutrons, which are called nucleons. Protons have a positive charge, and its relative charge is +1. Neutrons have no charge, and its relative charge is 0. The mass of a proton and a neutron is similar. Around the nucleus, electrons orbit at high speed. Electrons have a negative charge, and its relative charge is -1. Mass of an electron is about 1,800 times smaller than mass of a proton. So the relative mass of proton and neutron are 1,800. And relative mass of electron is 1. The number of protons, neutrons and electrons depends on the type of atom. An atom is normally electrically neutral. This means it has the same number of electrons as protons, resulting in a net charge of 0. The number of protons in an atom identifies the element. So atoms with the same number of protons are the same element. Nuclide notation. Nuclide notation describes the constituents of nuclei. X indicates the chemical symbol for the element. A indicates the nucleon number or mass number, which equals to total number of protons and neutrons. Z indicates the atomic number or proton number, which equals to the number of protons. For example of an atomic symbol for lithium. This denotes the chemical symbol of lithium. 3 is atomic number, meaning there are 3 protons in the nucleus. Since lithium is typically neutral, the number of electrons also equals the number of protons, which is 3. 7 represents the mass number or nucleon number. So the number of neutrons equals 7, minus 3 is equal to 4. Isotopes. Isotopes are atoms of the same element that have an equal number of protons, but a different number of neutrons or nucleons or mass numbers. This means that each element can have more than one isotope. Hydrogen, the simplest element, serves as a great example. It has 3 main isotopes. Hydrogen 1 or protium. It has 1 proton, 0 neutron and 1 electron. Hydrogen 2 or deuterium. It has 1 proton, 1 neutron and 1 electron. Hydrogen 3 or tritium. It has 1 proton, 2 neutron and 1 electron. They all have the same atomic number, 1 and the same chemical symbol, H. Isotopes of carbon. Carbon 12, it has 6 protons, 6 neutrons and 6 electrons. Carbon 13, it has 6 protons, 7 neutrons and 6 electrons. Carbon 14, it has 6 protons, 8 neutrons and 6 electrons. Isotopes tend to be more unstable due to their imbalance of protons and neutrons. This means they are more likely to decay. Unstable isotopes are the radioactive material that found in the environment, which causes the background radiation. For examples, carbon 12 and carbon 13 are stable isotopes, but carbon-14 is unstable isotopes. Carbon-14 found in the animals, plants, air, foods and others. Potassium-39 is stable isotopes and potassium-40 is unstable isotopes. Potassium-40 found in rocks, sea water, plants and others. Uranium-234, uranium-235, and uranium-238 are unstable isotopes. They found in rocks. Nuclear fission. Nuclear fission is the splitting of a large unstable nucleus into two smaller nuclei and releasing thermal energy. Nuclear fission happens in the nuclear power station and nuclear bomb. Isotopes of uranium and plutonium both undergo fission and are used as fuels in nuclear power stations. For example of nuclear fission by an uranium nucleus. A slow-moving neutron is absorbed by a nucleus of uranium-235. The uranium-235 nucleus is called the parent nucleus. The nucleus becomes highly unstable of uranium-236 and splits into two lighter nuclei of krypton-92 and barium-141. The krypton and barium nuclei are called the daughter nuclei. Then, 3 neutrons are ejected and burst of energy is released. The krypton and barium nuclei and 3 neutrons are called the products. The energy released by the mass of the products, the krypton and barium nuclei and 3 neutrons, is slightly less than the mass of the original uranium-236 nucleus. This lost mass is converted to energy. This is because the mass-energy equivalence with Albert Einstein's famous equation as E = mc², which means that mass can be converted into energy and vice versa. If the emitted neutrons go on to split other nuclei, and so on. The result is a chain reaction, and a huge and rapid release of energy. Nuclear fusion. Nuclear fusion is the combining of 2 light nuclei to form a heavier nucleus and releasing thermal energy. This process requires extremely high temperatures and pressures to maintain. This is why nuclear fusion has proven very hard to reproduce on Earth. Nuclear fusion is used to create the energy in the stars and sun. Most stars, including our sun, shine brightly thanks to a powerful process called nuclear fusion. 2 hydrogen isotopes, deuterium, or hydrogen-2, and tritium, or hydrogen-3, are fused together to form helium-4, releasing a neutron and burst of energy. The deuterium and tritium nuclei are called the parent nuclei. The helium-4 is called the daughter nucleus. An helium-4 nucleus and a neutron are called the products. The energy released by the mass of the products, the helium-4 and a neutron, is slightly less than the mass of the parent nuclei, the deuterium and tritium. This lost mass is converted to energy. This is because the mass-energy equivalence with Albert Einstein's famous equation as E = mc², which means that mass can be converted into energy and vice versa. The products of helium nuclei can also fuse together to create the heavier nucleus, the result in a chain reaction. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Background radiation. Radiations are alpha particles, beta particles and gamma rays. This is also called nuclear radiations. The background radiation is a small amount of radiation around us all the time, because of radioactive materials in the environment. Background radiation comes from sources both natural and artificial in our environment. Naturally occurring radioactive materials are present in our surroundings, including rocks, soil, air, building materials, food and drink, and even space itself. These natural sources contribute to the majority of background radiation we encounter. Artificial sources, such as medical equipment and waste from power stations. The proportion of sources of background radiation in the environment as shown on the diagram. Radon gas in the air is the primary source of background radiation. It comes from the ground due to the natural decay of uranium in rocks and soil. Rocks, soil and building materials. Naturally occurring radioactive elements like uranium and thorium are found in rocks and soil. These elements decay over time, releasing radon gas and contributing to background radiation. Natural radioactivity can be found in building materials, including decorative rocks, stone and brick. Medical sources. Medical procedures like X-rays, CT scans, and radiation therapy utilize radiation, contributing a small portion to background exposure. Food and drink. Living plants and animals contain radioactive elements, including carbon-14, within their bodies, which contribute to background radiation. Cosmic rays from space. The Sun constantly emits protons, some of which collide with Earth's atmosphere, creating gamma rays that contribute to background radiation. Ionizing radiation. When unstable nuclei decay, they give out ionizing radiation. When ionizing radiation collides with an electron in the atom, it ejects an electron, and the atom becomes a positive ion. Ionizing radiation causes atoms to gain or lose electric charge, forming ions. This is called ionizing effect. Other forms of ionizing radiation include ultraviolet and X-rays. If a gas becomes ionized, it will conduct an electric current. In living things, ionization can damage or destroy cells. Detection of radiation. Nuclear radiation is measured using a Geiger-Müller tube connected to a counter. Count rate is the number of decays per unit time detected by a detector and recorded by the counter. The structure of Geiger-Müller tube is shown. It is measured in counts per second or counts per minutes. The window at the end is thin enough for all radiation to pass through. If a radiation enters the tube, it ionizes the gas inside. This sets off a high voltage spark across the gas and a pulse of current in the circuit. When the radiation from a radioactive source is measured, the reading always includes any background radiation present. So an average reading for the background radiation alone must also be found and subtracted from the total. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. The three types of nuclear emission. Nuclear radiation is emitted from the radioactive decay of unstable nuclei. There are three main types of nuclear radiation: alpha particles, beta particles and gamma rays. The alpha particle is the helium nucleus, containing 2 protons and 2 neutrons. Therefore its symbol is He42, or alpha 42. Beta particle is high-speed electron emitted from the nucleus. Therefore, its symbol is E0-1, or beta 0-1. Gamma ray is electromagnetic wave emitted from the nucleus. Therefore, its symbol is gamma. Relative charge of alpha particle is positive 2, because it has 2 protons. Relative charge of beta particle is negative 1, because it is electron. Relative charge of gamma ray is 0, because it is electromagnetic wave. Relative mass of alpha compared with mass of an electron is approximately 7,200. This is because each proton and neutron is about 1,800 times heavier than an electron. Relative mass of beta is 1, equal to the mass of an electron. Relative mass of gamma is 0, because it is electromagnetic wave that has no mass. Average speed of alpha is up to 0.1 times the speed of light. Average speed of beta is up to 0.9 times the speed of light. Average speed of gamma is equal to the speed of light. Ionizing effect of alpha is strong. This is because it is heavy mass, low speed and high charge. Ionizing effect of beta is weaker than alpha. This is because it has lower mass, higher speed and lower charge than alpha. Ionizing effect of gamma is very weaker than alpha and beta. This is because it has no mass and charge, and high speed than alpha and beta. Penetrating effect of alpha is very short range. It is stopped by a sheet of paper, skin, or a few centimeters of air, around 5 centimeters. This is because the alpha has strong ionizing effect. Penetrating effect of beta is greater range than alpha. It is stopped by a few millimeters of aluminum or other metal, around 5 millimeters, or by a few meters of air. This is because the beta has less ionizing effect than alpha. Penetrating effect of gamma is very long range. It never completely stopped, though lead and thick concrete will reduce its intensity. It can travel through air for several kilometers. This is because the gamma has very weak ionizing effect than alpha and beta. Effects of nuclear radiation in an electric field. When a radioactive beam travels through a uniform electric field, the different types of radiation separate due to their charges and masses. The alpha particles are deflected towards the negative plate. This is because the alpha has a positive charge and is attracted to the negative plate. The beta particles are deflected towards the positive plate. This is because the beta has a negative charge and is attracted to the positive plate. The gamma rays are not deflected. This is because they have no charge. The alpha is less deflected due to its heavy mass, even though it has a higher charge. Mass has a stronger influence on deflection than charge in this case. Therefore, the beta is more deflected due to its less mass and charge. Effects of nuclear radiation in the magnetic field. When a radioactive beam travels through a uniform magnetic field, pointing directly into the page, the different types of radiation separate due to their charges and masses. The alpha particles are deflected in a circular path upwards from the page. This is because the positively charged alpha particle creates an electric current in the direction of its motion. This current interacts with a magnetic field to create the force acting on the alpha particle upward, as it enters the magnetic field. To determine the direction of this force, we can use Fleming's left-hand rule. Middle finger points in the direction of the current, along the alpha's motion. Index finger points in the direction of the magnetic field, into the page. Thumb points in the direction of the magnetic force, upward. Since the magnetic force is always perpendicular to the alpha's motion, it causes the particle to travel in a circular path upwards. The beta particles are deflected in a circular path downward from the page. This is because the negatively charged beta particle creates an electric current in the opposite direction of its motion. This current interacts with a magnetic field to create the force acting on the beta particle downward, as it enters the magnetic field. To determine the direction of this force, we can use Fleming's left-hand rule. Middle finger points in the direction of the current, opposite to the beta's motion. Index finger points in the direction of the magnetic field, into the page. Thumb points in the direction of the magnetic force, downward. Since the magnetic force is always perpendicular to the beta's motion, it causes the particle to travel in a circular path downwards. The alpha is less deflected due to its heavy mass, even though it has a higher charge. Mass has a stronger influence on deflection than charge in this case. Therefore, the beta is more deflected due to its less mass and charge. The gamma rays are not deflected. This is because they have no charge. Experiment to determine the amount of nuclear radiation emitted from a radioactive source. First method, to measure the background radiation count rate using a Geiger-Müller tube. The results are shown in the table. Therefore, the average background radiation being 20 counts per minute. The value of background radiation may vary over time due to the random nature of radioactive decay. Second method, to measure the count rate of the radioactive source without an absorber. Place the radioactive source close to the GM tube, because alpha particles can only travel about 5 centimeters through air. The results are shown in the table. Therefore, the average count rate being 560 counts per minute. Since the count rate of radiation from the source is 540 counts per minute after subtracting the background radiation. Third method, to measure the count rate of the radioactive source with paper, as shown in the diagram. Paper only stops alpha particles, so their count rate will not be detected by the GM tube. If the average count rate is approximately equal to the background radiation, it means all the source's radiation was alpha particles. If the average count rate is more than background radiation, but less than 560 counts per minute, then some of the source's radiation is alpha, while the rest is beta or gamma. For example, the average count rate is about 250 counts per minute, so the count rate of alpha is 310 counts per minute, and the rest is beta or gamma as 230 counts per minute. If the average count rate is approximately equal to 560 counts per minute, then no alpha particles are emitted from the source, while the rest is beta or gamma. Fourth method, to measure the count rate of the radioactive source with thick aluminum. Thick aluminum stops both alpha and beta particles, so their count rates will not be detected by the GM tube. If the average count rate is approximately equal to background radiation, meaning the count rate of source has no gamma rays. If the average count rate is more than background radiation, but less than 560 counts per minute, then some of the source's radiation is gamma rays, while the rest is beta or alpha. For example, the average count rate is about 250 counts per minute, so the count rate of alpha or beta is 310 counts per minute, and the rest is gamma as 230 counts per minute. If the average count rate is approximately equal to 560 counts per minute, then all of the source's radiation is gamma rays. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Radioactive decay. The most stable nuclei have roughly the same number of protons as neutrons. Therefore, if a nucleus has an imbalance of protons or neutrons, it is more likely to decay into small nuclei until it gets to a stable nucleus with roughly the same number of each. Therefore, isotopes of an element may be radioactive due to an excess of protons or neutrons in the nucleus, the nucleus being too heavy. Radioactive decay is a random process. This means we cannot predict which specific nuclei will decay, but each nucleus has the same probability of decaying within a certain time frame. Radioactive decay is also spontaneous, meaning it occurs without any external influence. Factors like temperature and pressure do not affect the decay itself. Alpha decay. In alpha decay, a heavy unstable nucleus breaks apart to emit an alpha particle, which consists of 2 protons and 2 neutrons. This results in the number of protons decreasing by 2 and the number of neutrons decreasing by 2, leading to a loss of 4 nucleons overall. Parent nucleus X with atomic, or proton, number Z, and mass, or nucleon, number A. Undergoes alpha decay, emitting an alpha particle and transforming into a new daughter nucleus, Y, with 2 fewer protons and 4 fewer nucleons. It is important to remember that the total number of nucleons and protons must be conserved in a nuclear reaction. This means the sum of nucleons and protons on both sides of the decay equation must always be equal. For example, an unstable radium nucleus with 226 nucleons, 88 protons, and 138 neutrons. When it undergoes alpha decay, it emits an alpha particle and transforming into radon nucleus with 222 nucleons, 86 protons, and 136 neutrons. This is called the decay products. During alpha decay, the top numbers balance on both sides of the equation. 226 is equal to 222 plus 4. So the nucleon number is conserved. The bottom s balance on both sides of the equation. 88 is equal to 86 plus 2. So proton number is conserved. A new element is formed, with an atomic number 2 less than before. The mass number is 4 less than before. Beta decay. In beta decay, an unstable nucleus changes a neutron into a proton, and then emits an electron. This results in the number of protons increasing by 1 and the number of neutrons decreasing by 1, keeping the total number of nucleons the same. Parent nucleus X with atomic, or proton, number Z and mass, or nucleon, number A, undergoes beta decay, emitting a beta particle and antineutrino, and transforming into a new daughter nucleus Y with 1 higher protons and remaining nucleons. For example, an unstable iodine nucleus with 131 nucleons, 53 protons, and 78 neutrons. When it undergoes beta decay, emitting a beta particle, an antineutrino, then transforming into a xenon nucleus with 131 nucleons, 54 protons, and 77 neutrons. During beta decay, the top numbers balance on both sides of the equation. 131 is equal to 131 plus 0, so the nucleon number is conserved. The bottom s balance on both sides of the equation. 53 is equal to 54 minus 1 plus 0, so proton number is conserved. A new element is formed, with an atomic number 1 more than before. The mass number is unchanged. Gamma decay. An unstable nucleus with excess energy emits gamma rays to reduce its energy. This process does not change the number of protons, neutrons, or nucleons. As a result, the nucleus remains as the same element, but with lower energy. It does not transform into a new element. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Half-life of radioactive isotope. It is the time taken for the nuclei of that isotope in any given sample to decay to a half its original value. Activity and half-life. Activity of radioactive sample is the average number of disintegrating per second. The SI unit of activity is the becquerel. Since the activity is always proportional to the number of undecayed nuclei, therefore, half-life has another meaning. It is the time taken for the activity of any given sample to fall to half its original value. A GM tube is used to detect the nuclear radiation emitted by the sample of iodine-131, and then the background radiation is subtracted. The number of count rate per second recorded by the counter is proportional to the activity, but not equal to it, because not all of the emitted radiation are detected. The graph shows the activity of a sample of iodine-131 varies with time, excluding background radiation. Its activity halves every 8 days. So, the half-life of iodine-131 is 8 days. Radioactive decay is a random process, so in practice, the curve is a best fit of data points that vary irregularly as shown. The graph shows the activity of a sample of iodine-131 varies with time, including background radiation. From the graph, we can estimate the background radiation to be approximately 10 counts per second, as the decay curve cannot fall below this value. The initial activity is approximately 50 counts per second. Therefore, the initial activity of the radioactive sample is 50 minus 10, which is 40 counts per second. Half of the initial activity of the radioactive sample is 20 counts per second. Adding the background radiation to 20 gives us 30 counts per second. This point can be marked on the graph to indicate the half-life of iodine-131, which is 8 days. Uses of radiation. Smoke detectors. Alpha particles are used in smoke detectors. This is the alpha source. It emits the alpha radiation that pass through air between charged plates. The alpha radiation will ionize the air particles, creating negatively charged electrons and positively charged ions. These charges get attracted to the charged plates, causing the current to flow. The detector senses this current. When smoke enters the detector, it blocks the alpha radiation, reducing ionization and current to decrease. If the current drops below a certain threshold, the detector interprets it as an indication of smoke and triggers the alarm. If beta or gamma radiation were used in this situation, then they would pass straight through the smoke and the alarm would not go off. Therefore, since alpha is absorbed by smoke, and beta and gamma are not, this makes it most suitable for use in a smoke detector. Measuring the thickness of materials. As a material moves above a beta source, the particles that are able to penetrate it can be monitored using a detector. If the material gets thicker, more particles will be absorbed, meaning that less will get through. If the material gets thinner, the opposite happens. This allows the machine to make adjustments to keep the thickness of the material constant. Beta radiation is used because it will be partially absorbed by the material. If alpha particles were used, all of them would be absorbed and none would get through. If gamma were used, almost all of it would get through and the detector would not be able to sense any difference if the thickness were to change. Diagnosis using gamma. Radioactive isotopes are used as tracers to help doctors identify diseased organs, like the kidney or the liver. A radioactive tracer is a chemical compound that emits radiation. The tracer is taken orally by the patient or injected. Its journey around the body can then be traced using a gamma camera to detect the emissions from a tracer to diagnose cancer and determine the location of a tumor. Different chemical compounds are chosen for different diagnostic tasks, depending on the organ or function being evaluated. A short half-life is important as this means that the activity of the tracers decreases to a very low level in a few days, thereby ensuring the safety of the patient. Treatment of cancer using gamma radiation. Radiotherapy is the name given to the treatment of cancer using radiation. Radiation can kill living cells. Some cells, such as bacteria and cancer cells. Beams of gamma rays are directed at the cancerous tumor. Gamma rays are used because they are able to penetrate the body, reaching the tumor. The beams are moved around to minimize harm to healthy tissue whilst still being aimed at the tumor. Sterilizing medical equipment. Gamma radiation can kill bacteria and viruses. It is used to kill the microorganisms on surgical instruments and other medical equipment. This technique is called irradiation. The items to be sterilized are placed in secure bags to ensure that they cannot be recontaminated before use. The gamma radiation will pass through the packaging and destroy bacteria without damaging the item. Sterilizing food. Food can be irradiated in order to kill any microorganisms that are present on it. This makes the food last longer and reduces the risk of foodborne infections. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Effects of ionizing radiation on living things. Ionizing radiation can damage human cells and tissues at high doses, resulting in cell death, tissue damage, mutations, and cancer. As a result, its use needs to be minimized. Cell death and tissue damage. Radiation can kill living cells and is effectively used to destroy cancerous tumor cells. However, it can cause damage to healthy tissue if it is not properly targeted, particularly from high-energy radiation, such as gamma rays and X-rays. Mutations leading to cancer. If the atoms that make up a DNA strand are ionized, then the DNA strand can be damaged. If the DNA is damaged, then the cell may die, or the DNA may be mutated when it reforms. If a mutated cell is able to replicate itself, then a tumor may form. This is an example of cancer, which is a significant danger of radiation exposure. Acute radiation exposure can have other serious symptoms. It can cause skin burns, similar to severe sunburn. Radiation can reduce the amount of white blood cells in the body, making a person more susceptible to infections by lowering their immune system. Safety precautions. To mitigate the risks of radiation exposure, there are some safe practices that should be used. Store the sources in lead-lined boxes and keep at a distance from people when not in use. Handle radioactive materials only while wearing gloves and using tongs to increase the distance from them. Minimize the amount of time you handle sources for and return them to their boxes as soon as you finish using them. During use, keep yourself and others as far from the sources as feasible. Consider wearing protective clothing to prevent body contamination. Limit the time that a radioactive source is being used. Radioactive waste with a long half-life is buried underground to prevent it from being released into the environment. I hope you found this video helpful. If you did, I would be grateful if you would subscribe, share, like and leave a positive comment. Your support will encourage me to create more content. Thank you.